Okay, so in this tutorial, I'm going to show you how to write a recursive function. And I'll do that by comparing it, comparing recursion with iteration. So we'll take a simple task like counting to 10, and we will implement that iteratively and then recursively. And then I'll dive into like what's going on in both cases in the internals of your machine. And then, I'll mention some applications that are maybe a little more realistic and things I will probably explore in future videos. So let's count to 10 iteratively first, and we'll use a while loop. So let's just say count equals 0. So this will be our starting point. And let's just call the maximum, we'll call that limit. So 10, right? And so we can say while count is less than or equal to limit, print count equals count plus 1. So when I run this, it should basically print out 0 through 10 and then stop. Notice this less than or equal to. So this allows us to essentially get to 10, print it, increment it, and then when it hits 11, it will essentially terminate. There we go. So 0 through 10. You could also do this with a for loop. That would be iterative as well. You could say for n in range 10. Actually, we'll say 11 because when you use the range function, the implicit start is 0 unless you say otherwise, and then the end is the end is not inclusive, so it goes up to but not including whatever you pass in. So I pass in 11, it'll go up to including 11, so 0 to 10. So same thing, two different ways of doing the same thing. Arguably the for loop is a little bit cleaner. So that is how we would achieve counting from 0 to 10 iteratively. If we want to do it recursively, we're going to need a function. So that's one major thing that that's one major way in which recursion differs, is that you need to use a function for recursion. So let's say we'll call our recursive function count up, right? And we'll say we'll give it 2 arguments, the current value and then the limit, right? So our goal here is to do the exact same thing, count from 0 to the limit, including the limit. So let's say we'll check on each count up call if current is, let's see, the limit, if the current value is greater than the limit, we want to return, right? So we want this function to eventually terminate at some point. So return, just to, I should maybe mention this, but like when we call count up and we return, eventually that function call needs to be returned to our code so we can proceed with the rest of the code. So that's what would be going on here. And if the current is not greater than the limit, we want to do what we were doing before, which is print current. And then this is the trick of recursion. So now we're going to do something slightly mind-bending if you haven't seen it before. But we're going to do count up. We're going to call count up within the count up function. And we're going to pass it 2 values. We're going to pass it current, but we're going to add 1 to it. And we're going to pass it limit, which essentially stays the same. So here we go. We have a function that's been defined. We haven't called it yet. But if we do call it, we need to give it some initial arguments. So at this point, we can define them. We can say 0 will be our current, right? And then limit will be 10. And this should essentially print out the same output as the while loop. Sweet, it worked. As you can see, our output with the recursive method is the same as the iterative method. So how do these actually differ? Basically what we're doing here is we are defining a function, and then when we call it, let's say on the first time through, it's checking current greater than limit, and if it is so, it returns, which isn't going to happen for us because we really have a ways to go before we get to 10. So we're going to print it, and then this is a crucial part. We're going to, instead of returning a value, we're going to call the same function within the original function again, passing in one more than the previous current value and the same limit, right? So I think at this point, especially if you're new to this notion of recursion, there's a major difference between the iterative method and the recursive method emerges, because with the iterative method, I think it's somewhat intuitive in that you don't really sit there thinking, questioning what is iteration when you look at this while loop, because it's sort of transparent. It says while this condition count is less than limit, while that condition is true, execute the code, and then it's going to go back and check that value again. It's going to keep going. And for n in range, it's sort of basically the same thing. But with recursion, you know, our mental model of how this works, especially like our naive model, is, I would say, seems it's obliterated, because you don't really know what count up does when you call it from a function. At least it wasn't obvious to me, and I think it depends even on the implementation of the language. So I think the best way to think about it is, it's like if you think about count up the first time it's called, right? Now it goes through these first 3 lines, and then it calls count up again. But I want to make it clear that this is now executing. So the first count up hasn't actually finished executing. So we now have another count up that's running as part of the original count up. And then in this second count up, and this is where it starts to hurt your brain, that runs the same instructions, and it gets to another count up. And because we haven't reached the limit, this count up is now running inside of the previous function, which is running inside of the previous function. So that is essentially how it's working. And I think just explaining it alone is sort of a tongue twister. So I'm going to use this excellent tool written by Philip Guo called Python Tutor to show us in a little bit more clarity what's going on when we call a function that's recursive. So first, I'd like to actually explore the while loop just as a point of comparison. So we'll say, let's see, count equals 0 and limit equals 10, while count is less than or equal to the limit, print count equals count plus 1. So looks like it's running it for us in real time. Oh, I see. It's highly experimental. We're in the live programming mode. I forgot about this, but doesn't really matter. We can just go back here. So if we step through each line, it's going to move just sequentially down on the left according to where the arrow is. So we'll step forward, and what we see here is once count's executed, it's made some space for us inside of this global frame, which you can just think of as like a main function that all of our code runs in. And then let's see, we define limit as 10. And now we hit this while loop. So this is where the difference really, really happens between iteration and recursion. So check this out. So let's see. We just keep running lines 4, 5, 6 over and over again, right? And each time this count is changing. And we print the output. Let's see, so we're getting close. Counts 9, counts 10, so it's still valid. And then, we hit 11. So notice we're at line 4 where this condition is checked. So limit right now is 10 and count is 11. So this is going to evaluate to false because count is not less than or equal to limit, right? So we've finished essentially, as you can see down here. And so this is basically what we get. We have our output, which same as what we had before. And we have our variables that have essentially are not being changed at all. And let's see. So one thing I might mention, this isn't exactly relating to iteration, but in other languages like C or Java, the while loop would create what is called a separate scope, in the sense that it's its own little environment with its own variables that are essentially private from the outer environment. And so when the while loop in C finishes, those variables are not really around. So in C, if you did this, you'd have count equals 0, and then inside the loop, count would increment all the way to 11, then stop. And if you printed out count, you should get 0 again, because the count inside the loop is different than the count outside of the loop. And that's what I mean by scoping. So in C, if you print count, you should get 0. In Python, you don't. You get 11. And that's because this count sticks around after the while loop. Anyway, that's a digression, but it is a gotcha sometimes, and I'm not sure if it's a feature or a bug, but anyway. So we've seen with the iterative method, we have a little block here of blue, right? And it's one frame. We didn't require more than really one function. So this is going to change drastically when we implement the recursive method. So let's take this code for the recursive method, put it in here. Okay. So we haven't called it yet, but what we have is our definition, which we saw before, right? So there's our function. And what happens here is in the global frame, it just binds the name count up to some procedure that will be run once we call it, right? So it's really only just one step here. Okay, now if we do call count up, right, we want to give it 0, give it a max of 10, right? So let's step through this, see what's actually going on. So let's see, we've already allocated the space for the function. Now when we call this, let's see, we get a different function, right? And this is sort of what we expect, because we called a function within the other function. Actually, it's not what we expect. This is exactly what I'm trying to explain, is this notion of what actually happens in recursion, because as I was saying before, I don't think it's it's not very clear when you look at it, and it's sort of like a mental, it's almost like a riddle. So what goes on here is that we have this original function, the global frame, but because, and this thing is still running when this new function shows up. So it's, I think the way it works is basically the compiler, or the thing that allocates space for your code, uses a data structure called a stack when it runs functions. So previously we had just one function, and there wasn't really any need to add or remove functions. But now we have, we're calling more functions. So every time a function is called, we put it on the stack. So you can think of a stack as like essentially just, it's called a stack because it's pretty aptly named. So imagine like a stack of books. You put down a book, you put down another book, put down a third book. And so the rules of a stack are you can't just go and get the second book. You have to essentially pop off the third book, or the top. It's always popping off the top to remove that item. So if you want to get all the way down to your first function or your first book, you need to, all of those other books need to be popped off the stack first. And what corresponds to popping or taking a book off the top is a function returning, right? So let's just, I'll return to this in a second, but let's just run through this to see what it looks like when you recurse. So, right, so yeah, so you can see here, every time current is incremented, which is essentially a new function call, we get a new function on a stack. So unfortunately this is going down, but I think it's more natural to think of it as going up. Yeah, so if we keep going through, we run the code, and notice each time it's executing inside of this countup function because we haven't reached the terminating case. So if you notice, it never goes to line 4. It always goes from 3 to 5. All right, so what we're looking at here, if we keep going now, so current is 10 and limit is 10. So we have a little bit more to go, but not much further. So we're gonna hit 11 and it's gonna check, let's see where we are. Right here, we're at this check, basically the terminating case. In recursion, this is called a terminating condition or a base case, and this is a very important aspect of recursion because if you get this wrong or you don't have it, the function will run forever. So that's, I think, one thing to consider when you're writing a recursive function is always, what is my terminating case, and will this actually make my function or my recursive, function terminate? So we're right up on it, where the moment of truth has arrived. So, so we did reach 4 on this one because the base case engaged and we returned from countup. So, yeah, so this is an interesting part. So you might think that's the end, right? So once we finally reach return, that's the end of this, but it's actually not the case. So what happens is, okay. So we hit 11 here, current's 11, so that triggers this return value. So as I said before, what's happening each time we call countup is that it's occurring inside of another function. So essentially, each one of the functions before the one that triggers this return value is still running. They all just have nested functions inside of them. So essentially, like, I guess the way people usually describe this is this winding phase and this unwinding phase. So what we've done is we've just visualized the winding phase, which is essentially building up the stack of functions all the way to the point until a base case is reached, right? So now when we hit 11, when current is 11, we return. And since this is the most inner function of all of these nested functions, now this function returns. So that lets the one previous to it return, which lets the one previous to it return, which lets the one previous to it return, all the way down till we get to the original count up call, right? So if we look at this, it's not the best. It's sort of difficult to show you, but if I move forward, we have a return value here, right? Which is just what I was talking about. So now everything gets, so this return value gets propagated from the most inner function all the way back to all the functions that called it, right? So this is called the unwinding phase. So all these functions have just been sitting there waiting for a value, because essentially when you call countup inside of countup, this is going to run another function, but this thing is still waiting for something, because this is a process that is going on inside of it. And now we get all the way back. So I will basically I'll try to get to the point right where this function resolves. So right here. Now we pop it off. So this is the stack, all the things being popped off the stack. And now we're back in the global frame. And this is basically the termination, the complete termination of a recursive function. So sadly, we didn't actually return a value. We could have returned like, yay. But we didn't. So let's see if it'll actually. Yeah, so we returned yay, and yay means we are going to get to go home again, all the way back to the original calling function. So I hope that this was somewhat useful to you in terms of just coming up with a mental model of how recursion works, because it is really, as I've said probably 5 times, it's not intuitive. But I think the best thing to think about when you're calling a recursive function is to think, when you call a function within itself, that outer function is still running until the inner one finishes, because it's just how we process lines of code in Python. We don't process print current until this runs. So I mean, it might take nanoseconds to run this, but it's still it's called synchronous execution. And so this runs, then this runs, then this runs, right? So there's no way for this to return without this returning. Anyway, so I think that basically covers recursion. And so you might wonder, like, why use recursion? Why would I need? I think it amounts to, let's see, 11 function calls for 0 through 10, and then another one to check 11. So that's 12 function calls plus the global frame. So it's 13 functions the most functions at any one point is 13. So why do we need 13 functions just to count to 10? And I would say you don't. You should do this iteratively. But the point I was trying to demonstrate is just how recursion works, how to think about it. But there are cases when recursion really simplifies some computation. So using, like, you could do calculating some Fibonacci sequence recursively, and it lends a bit of elegance to your code. It makes it sometimes more succinct and more compact and just self-defined. Another reason why you'd want to use recursion is maybe if you're calculating the it it's very few lines of code, but it's very powerful. So anything that's hierarchical and like where there's a parent-child relationship, and like you say if you want to go from like your grandfather all the way down to your child or something, and you want to model this and calculate how many people were involved in that lineage, or something like that. Anything that's tree-like with hierarchy, recursion comes in very, it comes in handy. So so in future tutorials, I will probably actually demonstrate maybe some more sophisticated uses of recursion, so we can use it to sum a bunch of numbers. We'll do some Fibonacci stuff, and then I think I'll dive into some tree stuff with recursion. So thanks for watching.